possesses three different types of energies, and these energies are: number one, kinetic energy. Okay, let's call this in short Ke. And we already know the expression for kinetic energy. Kinetic energy is half mv squared. This is a well-known expression. Okay, so let us do one thing. Let us divide by mass so as to get the kinetic energy per unit mass. So if we divide by mass, this mass will vanish from the right hand side, so you will get v squared by 2. Okay, so that's the first type of energy possessed by a liquid in motion. The second type of energy is potential energy. Imagine the pipe is at some height above the ground, so it will have gravitational potential energy PE, and we already know the expression for the potential energy mgh. Okay, so again here we will find the potential energy per unit mass. That means we are dividing it by mass on both sides. This mass will vanish, so you get only gh. Okay, and number 3, pressure energy. Okay, so this pressure energy is equal to the pressure into volume. So therefore, pressure energy by mass, this will be PV divided by mass. But we know very well that mass by volume is nothing but the density. So you have pressure by density, since density is mass by volume. All right, so these are the three types of energies. Okay, so kinetic energy is the energy possessed by the liquid because it is moving, it is in motion. Potential energy is the energy possessed because the pipe, let's say, through which the liquid is flowing is at some height above the ground. And pressure energy, we know that whenever water flows through a pipe, there is pressure inside. Yes, so how do we know that? Suppose if you have a pipe, I think you have seen this many times, right? If there is a leakage in the pipe, let's say water is flowing inside, okay? So if there's a leakage in the pipe somewhere here, then you can see that water comes out like that, right? So why does water comes out of there? And sometimes it goes very far, it goes very high sometimes. Why? Because the pressure out here is quite high. Okay, so we can understand that when the water is flowing inside the pipe, there is pressure also. And that energy which is due to the pressure is called pressure energy. The Bernoulli's theorem is the outcome of the principle of conservation of energy applied to a liquid in motion. Now, the statement of this theorem is as follows. For a streamlined flow of an ideal liquid, the total energy, that is the sum of kinetic energy, potential energy, and pressure energy per unit mass, remains constant at every cross-section throughout the liquid flow. That is, mathematically we can write, that is, kinetic energy per unit mass is V squared by 2 plus potential energy per unit mass is GH plus pressure energy per unit mass is pressure by density. This is constant. This expression is known as the Bernoulli's theorem. Let us prove this expression. As shown in this diagram, there is a pipe out here, the one drawn with gray color. This is a pipe having varying area of cross-section. So you can clearly see here that the area of cross-section is large. Let's call that A1. And here the area of cross-section is small. Let's call that A2. V1 is the speed of the liquid crossing A1, and V2 is the speed of the liquid crossing A2. P1 is a pressure at point X and P2 is a pressure at point Y. And you can see that the two levels of the tube are different. y is at a higher level, higher height h2, and x is at a lower height h1. Okay, now here, since this is an incompressible fluid and flowing steadily by the equation of continuity, okay, according to the equation of continuity, says that the speed is inversely proportional to the area of cross-section. So the smaller the area of cross-section, the larger will be the speed. So at this point where the area of cross-section is small, V2 would be large compared to V1. So therefore you have V2 to be larger than V1. Understand? So because V2 is larger, then what do you think will happen to the kinetic energy? Kinetic energy in a unit second. Okay, so you see here in 1 second, like I said, that this is incompressible fluid. So what will happen here in 1 second? In the same time, the same amount of fluid, or let's say liquid, will flow at this point and at this point, which means that the mass the mass of the liquid flowing at this point is equal to the mass of the liquid flowing at that point in 1 second. Is that clear? So if the mass is constant, then it all depends on the speed, right? And since V2 is larger than V1, then the kinetic energy passing through A2 will be larger than the kinetic energy passing through A1. So as this liquid is flowing from point X to point Y, what happened? It increased. There is an increase in kinetic energy. Is this clear here? So therefore the increase in kinetic energy per unit time, this will be what? This will be the kinetic energy where it is high. That means the kinetic energy at point Y minus the kinetic energy at point X. Okay, and what is the kinetic energy at point Y? So that will be half m v2 square minus half m v1 square. Let's call that some equation 1. Okay, let me explain to you again why I don't write here m2 and here m1. The reason is because the same amount of mass of the liquid will flow in the same time through this point and through this point. Okay, so that is the first equation. Now next, if we look at this, the level out here, this is higher level than this, yes or no? So can we say that the potential energy at Y will be larger than the potential energy at X? I think we can say that, right? Because potential energy depends on the height. The higher the body is, the more will be the potential energy. So as this liquid is going from a lower height to a higher height, what happened to the potential energy? It increased. Yes. So here also we will have increase in potential energy per unit time. This will be what? This will be potential energy at Y minus potential energy at X. Okay, and what is the potential energy at Y? That is mgh2 minus mgh1. Let's call this some equation 2. Now let us find where the pressure energy would be larger. So for that we need to find the force acting at this point and at that point. Okay, and we know that force is what? Force is pressure into area. So force acting at X, this will be the pressure at X, which is P1, and the area at X, which is A1. All right, so that is the force, and the force acting on Y will be P2A2, and we are going to write that a little bit later. So therefore work done per unit time. Work done per unit time by the liquid pressure. I'm going to cut short the words out here. We'll just say at X, this will be what? We know that work is force into displacement, right? So this will be P1 A1 into displacement. Displacement is what? Displacement S, this will be speed into time, right? Yes. So instead of S, we will write V1 into time, but time is what? Is a unit time, so time here is 1. Is that clear or not? And this is equal to what? Let's leave it okay, A1 into V1, and this is equal to P into volume. Yes. So why? Because this part is what? Is volume. We know that volume is area of cross section into the distance. Yes. So distance here is V1 into time. There is time also out here, okay, but then the time here is 1 second. So therefore the area of cross section into the distance per unit time, that will give us the volume per unit time, which is capital V, okay, and this is P1. So similarly work done per unit time at Y, this will be P2V. Got it? Now therefore change in work done, or you can say net work done, this is P1V minus P2V. Let's call this equation 3. All right. Now, didn't we say that this Bernoulli's theorem is a consequence of the conservation of energy? So by conservation of energy, net work done is equal to increase in KE per unit time plus increase in PE per unit time. So you have P1V minus P2V is equal to what was the previous expression? This one, half m v2 square minus half m v1 square. Half m v2 square minus half m v1 square plus increase in potential energy is what? Is mgh2 minus mgh1. mgh2 minus mgh1. Okay. Let's do one thing. Let's write the 1's on the left side and the 2's on the other side. So I have P1V, and this term, let me put it to the other side, and since this is a minus, it will become plus half m V1 square. Similarly, this one, I'll take it to the left side, it will become plus mgh1. And what will I do? I will take this to the other side, it becomes P2V. Then this will be there, plus half mv2 square, and this one plus mgh2. Then what do we do next? We are going to divide everything by mass. Okay, we'll divide both sides by mass. So dividing both sides by mass, you get what? Let's see. So I will get a mass out here. This mass will vanish here. This mass will vanish out here. So P1V by mass plus V1 square by 2 plus GH1 is equal to P2V by mass plus V2 square by 2 plus GH2. But then what is mass? Volume by mass, that is 1 by rho. So this will be P1 by rho plus V1 square by 2 plus GH1 is equal to P2 by rho plus V2 square by 2 plus GH2. Okay, so this means that it is a repetition, yes or no? So the terms on the left hand side are similar to the terms on the right hand side. The only thing different are the coefficients. Here we have coefficients 1. Here the coefficients are, the subscript, not the coefficient, 2. Okay, so if you write like this, it means that P by rho plus V square by 2 plus GH, this is constant. And that is the proof of the Bernoulli's theorem. Okay, right. Now the Bernoulli's theorem can be stated, or it can be written in some other form, in another form, dividing by G both sides. So if you divide by G both sides, you get P by rho G plus V square by 2G plus H, this is constant, by G is another constant. Okay, so these terms, they on the left hand side, they all have the dimensional formula of length, right? So that is why they are given a special name, head. Okay, head. So this is actually the pressure head. This one is called the velocity head. And this is the gravitational head. Okay, so you can say that the sum of the pressure head, velocity head, and gravitational head of an incompressible fluid flowing streamline is constant. That's another way to state the Bernoulli's theorem. So I want you to practice this derivation nicely, because it is important from the exam point of view. Thank you. Now let us discuss some phenomena which are based on this theorem, the Bernoulli's theorem. And before that, I want to discuss one concept first of all before we go into the discussion of the various phenomena. All right, so Bernoulli's theorem says that it is written like this. It is the equation is V square by 2 plus GH plus P by rho. This is constant. Okay. Now imagine if you have two stream of fluids. Okay, two stream of fluids which are flowing in the same height, at the same height. So in this case, height will be constant. Got it? So if height is constant, then we have just V square by 2 plus P by rho. This will be constant, because if I take GH to the other side, it will be constant plus constant or minus constant, which is another constant. All right, now this equation says that if it says that, you see here, the only variable quantity here is the speed and the pressure. Okay, the density of the same fluid, it would be the same. So this equation says that if the speed is high, then pressure will be low, in order for the right hand side to be constant. If one term increase, this term will decrease, and vice versa. So one important point that I want to note out here is this: if V is large, then the pressure is small. Okay, and vice versa. If V is small, then pressure will be large. Understand? So I think that is understood, yes or no? Because if you increase this, you have to decrease this part for this to be balanced out and come out to be constant. Got it? So if the velocity or if the speed is large, then the pressure has to be small. And if the speed is small, the pressure has to be large. So this is the basic idea. It is the basic idea of the Bernoulli's theorem. All right, and we are going to remember this when we discuss the different phenomena based on the Bernoulli's theorem. Okay, so the first phenomena that I want to discuss here is this one, the dynamic lift. Now, dynamic lift, in this diagram, you have the cross section of the wing of an aeroplane. Got it? The wing of an airplane. This is the cross section. Okay, doesn't look like an airplane, you might be asking me, but then the airplane wing is something like this. Yes, that's the airplane wing, and then you have the body of the airplane like that, right? Something like that. Okay, now what I do is you cut from this part. You cut from this part, and you will see the cross section of the wing of the aeroplane. So as this aeroplane is going in the forward direction, as it is going in this direction, what is happening is it cuts through the air, right? You can see this gray color lines that I've drawn. These are nothing but the air streams. Okay, the air streams. Got it? So the air streams will be going backward, right? It will be going like this in that direction. Okay. Now the design of the wing is such that the bottom part of the wing is flat, whereas the top part is curved like this. Understand? Now as this wing cuts through the air, the same air, it got splitted up and then it joins back here. So this one goes like this and joins back here. Understand? So you can see that the airstream that is going on top has to travel a longer distance because it has to take a curved path. The airstream that is going below is comparatively straighter compared to the one above. Understand? So this one is going along almost a straight line path. This one is going along a curved path. And because it is traveling a longer distance, what will happen to the speed of the airstream above this? It will be larger. Yes or no? So the airstream above will be going larger than the airstream below. So what will happen to the velocity out here or the speed here? The speed here will be large. Yes? And if the speed is large, the pressure is small. The speed below is small, and if the speed is small, the pressure is large. So that means that because of the different speeds of the airstreams above and below the wing, there is a difference in pressure. The pressure on top is small, the pressure below the wing is large. What will this large pressure do? It will push the wing upward. Okay? Because the pressure below is large, it will push towards the smaller value pressure. So as this wing, as this airplane is going forward, it gets lifted up. Okay? It gets pushed upward. Therefore, it gets lifted up. And that's how an airplane takes flight. Understand? It's basically it's basically due to the design of the wing. Got it? I think many of you have seen this or have observed this in the game of cricket, right? The swing of a cricket ball, right? So we used to be very fond of swing bowlers, right? And when we play also, we try to make the ball swing as much as we can because it really looks nice when the ball is taking a curved path in the air. Okay, so we are going to discuss the swing of a cricket ball. All right. Now in this diagram here, you can see this is a cricket ball. Okay, and these dotted lines out here, these are the thread of the cricket ball. Those of you who have seen the cricket ball, the deuce ball, there is a thread which is stitched because basically they are made of leather, right? So the two leathers are stitched together, and this is called the seam of the cricket ball. Okay, so people will hold from the seam, right? Will hold from the seam. Now, one thing you have seen that when a player or when a bowler is before he bowls, what happens is he uses a towel and he cleans the cricket ball nicely. He cleans the cricket ball nicely. Have you ever seen that or not? He cleans it nicely. He rub it nicely. He make only one part of the ball shiny. Okay, whereas the other part of the ball is made rough. Okay, so the swing of the cricket ball here, one thing is one part of the ball is always made to shine. It is rubbed nicely, and the other part is made to be as rough as possible. Got it? So when the ball is new, both sides will be equally shiny. The swing will not be there so much. But as the ball gets older, when it is about 3-4 overs old, then the ball gets older. Then after bouncing so much, rough patches appear on the ball. Then what happened here? You can make one side of the ball shine. Got it? Now, this is the physics behind actually how the ball is going. Okay, the ball is going forward, and what happened is it cuts through the air streams. Again, you can see these curved lines. These are the air streams. Okay, now have a look at these air stream on the left side. They are going over a rough patch. That means more friction. Here, the air stream is going over a smooth, shiny patch. Less friction. Yes, so because this is having less friction, this one will be traveling faster than this, is it not? Yes, this one is going smoothly. There is no resistance, there is no opposition to its motion. So this part of the air will be going faster. This one is going over a rough patch, so it will struggle a little bit. So therefore, it will move a little bit slower compared to this. So on the left side, the velocity is small. Okay, so if the velocity is small, what will happen to the pressure? Pressure will be large. And on the right side, the velocity is large. Pressure will be small. Got it? So because of this, there is a difference in pressure on the two sides of the ball. High pressure on the left side, low pressure on the right side. What will this high pressure do? This high pressure will push the ball like this. Got it? It will push the ball in that direction. So therefore, this ball, instead of going straight like this, it will travel a curved path like that. It will travel a curved path like this. Okay, why is it traveling a curved path? Because it is being pushed that way. Understand? So that is how the cricket ball swing. Got it? So this one, it is swinging towards the right side. Okay, now if you want the cricket ball to swing towards that side, what will happen? You make this part rough and this part you make it shiny. Is that clear here? So that's quite interesting, isn't it? The Bernoulli's theorem has a lot of applications, especially in sports. For those of you who watch football, on the other hand, do you know about the banana kick? Let me write it down here with yellow. The banana kick. Okay, this is a term that we use when we play football, right? So what is a banana kick? Banana kick is actually when you kick the ball and the ball goes in a curve in the air, right? Especially when you take an indirect kick, okay, or from the corner. You kick, the ball goes in the air, right? Sometimes if you're very good from the corner, you can make the ball go directly into the goal. Okay, that is called the banana kick. Now, what is the physics behind the banana kick, right? So the physics is this: the ball has to spin as it is traveling in the air. Okay, and like this ball is spinning like this as it is traveling. So this ball is actually going forward, and at the same time it is spinning. Okay, it is going this way, in that direction, and spinning in that direction. Now, due to the spin motion of the ball, you see here the air current, the air streams on the left side and on the right side of the ball. Now let us have a look at this part first. So this part, the ball is spinning that way and the airstream is going that way, it's going backward, right? So the spinning motion of the ball, it eases, that means it aids. It aids means it helps the airstream to go. That means it pushes the airstream. Got it? This one, because the ball is spinning that way, right? So this part will be pushed. It is aided by the spinning motion of the ball. So because of that, the speed of this airstream here will be large. Okay, and because the speed is large, the pressure is small or low pressure. Here, the airstream is going that way, the ball is spinning that way. It is spinning opposite to the direction of the airstream. So there is some resistance, right? So because of that, the speed of the airstream here will be small. And the pressure will be large. Understand? So you have, due to the spinning motion of the ball, you have difference in pressure on the right side. On the left side the pressure is large, whereas on the right side the pressure is small. So this large pressure, again, what will it do? It will push the ball in that direction, right? So as this ball is going like that, instead of going a straight path, it takes a curved path like that. Is that clear here? So this is known as the Magnus effect. Okay, now have you ever seen or not that when the wind is going very fast, it can blow off the roof of houses? Yes, so again that happens due to Bernoulli's theorem. All right, so here air is going very fast on top, so the speed of the air here, V, is large. Okay, so therefore pressure will be small. What about the air below? The air below is almost stationary. Yes or no? The air below the roof. So V here is small and the pressure is large. So this large pressure, it pushes the roof upward like this. Okay, so because it pushes the roof upward, then this wind can take off, it can blow off the roof. Okay, so those are the few phenomenon which are based on Bernoulli's theorem. Applications of Bernoulli's theorem. So in this video I'm going to discuss two applications of Bernoulli's theorem, and the first one is Torricelli's law of efflux, or sometimes called Torricelli's theorem. All right, now in this diagram, this is a tank. Okay, a tank which is filled with water up to a height y2. Got it? And somewhere here at a depth of h below the surface of the water, there is a small opening out here. This opening is called the orifice. Obviously, if there is an opening somewhere in the tank, the water will come out, it will gush out of this small opening, right? So this water will come out of the orifice with a velocity v1, and a1 is the area of cross-section of the orifice. A2 here is the area of cross-section of the tank, and it is very clear that A2 is very, very large compared to A1. All right. Now let us take 2 points in this diagram. Point 1, which is just near the orifice, and point 2, which is on the level of water. So because this part is exposed to air, the pressure of the water or the liquid here will be equal to the atmospheric pressure, PA. Right? So P1 here is equal to the atmospheric pressure, and this part of the tank is sealed. Okay, so therefore the pressure at this part, let us call it to be P. All right, so let us use the equation of continuity first. So we have two portions. Now one thing, what happened? If the water is let out of the tank, what do you think will happen to the level of the water here? As the water comes out, this level of water will keep on going down. Yes or no? Will decrease, right? So let's say the water comes out with velocity v1, that is the velocity of efflux, and the level of water goes down with velocity e2. Okay, so by equation of continuity, you have a1 v1 is equal to a2 v2, right? So v2 here will be a1 by a2 into v1. Now since a1 is very large compared to a2, so if a1 is very did I say a1? I'm wrong. Not a1, a2. Since a2 is very large compared to a1. Yes? So this area of the tank is so large compared to the area of the orifice. So in that case, what will happen to this ratio out here? This will be very small compared to 1, right? So therefore V2 will be approximately 0. I think this is physically true also, right? If you open the tap of the tank, as the water comes out, if you look at the level of water in the tank, of course it goes down, but then it goes down very slowly, as if it is not going down, as if this level is stationary, as if this level is just stuck out there, right? So therefore V2 we can assume it to be 0. Is this point clear? Got it. So now let us apply Bernoulli's theorem at points 1 and 2. Okay, so at point 1, what will be the expression for Bernoulli's theorem? Bernoulli's theorem, let me write it at the side out here. Okay, Bernoulli's theorem says P by rho plus V square by 2 plus GH. This is constant. Got it? So at this point 1, pressure is P1, right? P1 by rho plus velocity is v1, so v1 square by 2 plus g, and what is the height of this? y1, so gy1 is equal to let me do one thing. Let me write the expression at the level 2 first of all. It's okay. Let me continue with this. Okay, so that is at point 1. Now at point 2. At point 2, this will be P2 by rho. What is rho? Basically, rho is the density of the liquid out here. P2 by rho plus V2 square by 2 plus G. And what is the height of this level? Y2. Got it? But this term V2 is 0. So this term will be equal to 0. Understand? So we have V1 square. Let's do one thing. Let's do step by step. So P1 is actually PA. So we have PA by rho plus V1 square by 2 plus GY1 is equal to P2 is actually P by rho plus GY2. Okay, let me take a new page. All right, so this implies let me do one thing. Let me take this term and this term to the other side. So I will leave V1 square by 2 on the left side. So you have V1 square by 2. This will be what? It will be P minus PA. P minus PA by rho plus this minus this, gy2 minus gy1, take common g. So it will be g y2 minus y1. Got it? So v1 square by 2, this will be p minus pa by rho plus g. But what is y2 minus y1? If you look at the diagram, here, y2 minus y1 is actually h. And what is h here? H here is the depth of the orifice, not the height, okay? The depth of the orifice. That means the distance from the surface to the orifice. Okay, so this will be equal to h. Got it? So v1 square, this 2 will go up here. Let me write the gh in front. So you have 2 p minus pa by rho. So therefore v1, it will be 2gh plus 2 p minus pa by rho under a root. Got it? So this equation, have I marked an equation? No, let's call this some equation 1. This gives the velocity of the orifice. Okay, now a special case. Suppose this part is open. Okay, suppose this part is open. Now if the tank is open, let me rub off this part. Sorry about that. If the tank is open, then that means the tank will be exposed to the atmosphere, yes or no? So do you agree or not that P2 will also be equal to PA? Yes. So in that case, what will happen to this expression? Okay, so P will be equal to PA, so this part will not be there anymore. Got it? So if the tank is open, then P will be equal to PA. So therefore V1, this will be equal to 2GH under a root. Now what is this equation all about? This one. This actually is nothing but the equation, or sorry, it's nothing but the velocity of a body which is falling freely from some height. Okay, imagine you have a body, all right? Let's say a body which is falling from some height from rest. So this body is falling freely, and let's say it is falling from a height h. Got it? So what will be the velocity of this body just before reaching the ground? We use this formula, v square is equal to u square plus 2gh. Okay, and since it is falling from rest, this part will be 0. So v here will be root 2gh. You see here. So the velocity of efflux is same as the velocity of this body that is falling freely from the same height, from a height equal to the depth of the orifice. Are we clear here? So after deduction, and we take the special case if the tank is open, we get this equation. The velocity of efflux comes out to be root 2gh. But what is root 2gh? That is nothing but the velocity of a body falling freely from a height h. Okay, so from here we get the Torricelli's law, which can be stated as the velocity of efflux is equal to that which a freely falling body would acquire in falling through a vertical distance equal to the depth of the orifice below the free surface of the liquid. Okay, so that is the first application of Bernoulli's theorem. Let us go to this. The venturimeter is a device which is used to measure the rate of flow of liquid through a pipe. It is based on Bernoulli's theorem. So in this diagram, as you can see, it consists of a horizontal tube having a wider opening of area of cross-section A1 and a narrow neck having area of cross-section A2. these two regions of the pipe are connected to a U-shaped tube which is a manometer. And inside the manometer there is a liquid of density ρ1. Through the horizontal pipe, a liquid of density ρ is flowing. Okay, and let's say the speed of the liquid at this point is V1 and the pressure here is P1. Whereas the speed of the liquid in the narrow neck is V2 and the pressure in the narrow neck is P2. Okay, now from Bernoulli's theorem, we know that if the speed of the liquid, okay, first of all, let us look at the equation of continuity. What does the equation of continuity say here? All right, so equation of continuity says that if the area is small, the speed will be large, right? And vice versa. So here, where the area of cross-section is small, V2 will be large compared to V1. Is that clear here? So that's the first point that we have to consider. Now, secondly, the Bernoulli's theorem says that where the speed is large, the pressure will be small. Got it? So here, where the speed is large, pressure P2 will be small compared to the pressure P1. So that is the reason why here a small pressure is applied at this end of the manometer, a large pressure is applied at this end of the manometer. So this large pressure, it will push down this liquid. It will push down this liquid. So this liquid will go down at this end and it will rise up at that end. Okay, so depending on the pressure difference between this point and this point, the height also will vary accordingly. The difference in the height of the liquid in the manometer also will vary accordingly. Is that clear here? Okay, so now let us look at the working of this. Okay, so first of all, by equation of continuity, we have A1 V1 is equal to A2 V2. So from here we can find V2. V2 will simply be A1 by A2 times V1. Let's call this equation 1. Okay, right. Now let us apply the Bernoulli's theorem at the 2 points, at the 2 openings. Okay, so by Bernoulli's theorem, we have P1 by density of the liquid, which is rho, plus V1 square by 2. This will be equal to P2 by rho plus V2 square by 2. You might ask me, where is the third term? The third term is actually GH. Okay, but then since the height of this level and the height of this level is the same from the ground, so those heights, they get cancelled. Those 2 terms, they get cancelled. Understand? So we have only these 2 terms. Okay, so let's take this part to the other side. I will get P1 minus P2 by rho. Let's take this to the other side and I will get V1 square, sorry, not V1 square, V2 square. V2 square by 2 minus V1 square by 2. Got it? But this P1 minus P2 is the pressure difference between this point, and that is nothing but rho mgh. Okay, divided by rho. Let's put the value of V2 from equation 1. A1 square by A2 square, V1 square by 2 minus V1 square by 2. Okay, so we can take common V1 out here. So this implies rho mgh by rho, take common V1 square by 2, you will get A1 square by A2 square minus 1. Okay, so let's derive this some more. So V1 square by 2, this will be A2 square in the denominator, A1 square minus A2 square, right? So only V1 square, this term will go up, so you have 2A2 square rho m g h divided by this term rho a1 square minus a2 square. Okay, so therefore v1 will be square root of this square root, but then this a square is it can come out of the square root, so you have a2, then inside 2 rho mgh by rho a1 square minus a2 square. This goes under root. Okay, so this is the speed of the liquid inside the tube. All right, so what will be the volume of the liquid flowing per second? Volume of the liquid flowing per second is, let's denote it with Q. That will be A1 V1. So this will be A1 A2 and the term inside of the bracket 2 rho m GH by rho A1 square minus A2 square under a root. Got it? Okay, so knowing these values in the right hand side, we can find the speed of the liquid inside of the tube using this formula, and also the volume of the liquid flowing per second. So that is the working and the theory of a venturimeter, which is the other application of Bernoulli's theorem.